Welcome to the HT8 MCU Basic Tutorial. In this session, we will be exploring Comprehensive Experiment 1, Running Light. This experiment will be explained from the following 5 aspects, which are Running Light Experiment Introduction, Hardware Connections, Program Development, Practice Results, and Experiment Summary. Running Light Experiment Introduction. The learning objective of this experiment is to master the control of LED on/off using the general purpose I/O. Now, let's look at the experiment content. First, a 1.024 milliseconds interrupt is implemented using time base 0 for subsequent timing operations. Then, 6 LEDs are used to achieve a running light effect with a movement interval of 200 milliseconds. Additionally, 2 I/O pins are used for key detection. Key 1 controls the moving direction of the running lights, and Key 2 controls their pause and start. The knowledge points covered in this experiment include general purpose I/O, time base, internal oscillator, key scanning principle, and key debouncing. Let's see what materials are needed for this experiment. This experiment uses the DEV3195 development board as the main control board. The emulator provides the 5-volt power supply. We will also use the following components: LEDs, keys, resistors, a breadboard, a Type-C cable, and connection wires. Hardware connections. Next, let's go through the schematic diagram of this experiment. The main control MCU on the DEV3195 development board is the HT66V3195. A bypass capacitor is connected between the power supply and ground on the board, which helps stabilize the supply voltage and filter out AC noise. Since the MCU's general-purpose I/O pins can be configured with internal pull-high resistors, the I/O pins connected to the key should be set as inputs with input pull-high enabled. The VDD power supply is connected to the anode of the LED through a current-limiting resistor, while the cathode of the LED is connected to the MCU I/O pin. The LED lights up when the MCU I/O outputs a low level and turns off when it outputs a high level. For this experiment, we'll be using a breadboard. Below is the connection diagram for the setup. The power supply voltage VDD is 5 volts. You can find the programming pins on the upper side of the development board. For in-circuit emulation or programming, you can use either the E-Link Pro 2 or the E-Writer Pro 2 tool. Finally, here is a physical wiring photo of the breadboard for your reference. Program development. Now, let's look at the workflow within the MCU's main function. It includes the following steps in order: System clock configuration, WDT configuration, key I/O configuration and initialization, LED I/O configuration and initialization, time base 0 configuration, enable global interrupt, clear WDT, key scanning, LED event, and key event. The following describes the time base 0 interrupt function flow. The MCU enters the time base 0 interrupt every 1.024 milliseconds. Upon entering the interrupt flag is automatically cleared to 0 and the variable system_tick is incremented by 1. If the running light is detected to be in operation, the variable LED.LED_tick is incremented by 1. Next, let's look at the program example. Here is the main.c file. This experiment includes the HT66F3195.h header file. It contains definitions and declarations for the registers, ports, and peripherals of the HT66F3195 and HT66V3195 MCUs, which help us in programming. Macro definition and enumeration. Before developing the program, we typically use macro definitions to declare the pins that will be used to facilitate programming. These are the macro definitions for the key pins and LED pins. The key pins are configured as inputs while the LED pins are configured as outputs. This section defines the enumerations for key states, running light movement directions, and LED operating status. Struct and union. To facilitate management and clarify the code, all variables that implement a function are typically placed within a struct. Additionally, leveraging the characteristics of a union enables convenient unified management of multiple scattered variables. Function declaration. It informs the compiler about a function's name, return type, and parameter list. This is necessary to resolve compilation errors that occur if a function is called before it is defined. Variable declaration and definition. This creates a variable by informing the compiler of its name and data type, and allocates memory for it. Now, let's look at the main function. First, it performs the initial configuration. This includes setting up the system clock, the WDT, key scan initialization, LED initialization, and time-based zero initialization functions. Finally, it enables the global interrupt and enter the while loop. Inside the main loop, the WDT is first cleared to prevent a program timeout, followed by the sequential execution of the key scan function, LED function, and key function. Now, we will introduce the individual sections of the main function, starting with the system clock configuration function. It uses the internal oscillator and is set to 8 MHz. Next is the WDT configuration function. It enables the WDT and sets its overflow period to 512 milliseconds. If this period is exceeded, the MCU will reset. Therefore, it is important to clear the WDT regularly during program execution. Next is the time-based zero configuration function. The clock is configured with a 4 division of the system clock, that is, 2 MHz, resulting in a timing period of 1.024 milliseconds. Next is the key initialization function. Set the I/O of the two keys as input pull high, scan the initial state of the keys, clear the key press duration, and reset the key status. Next is the play key scanning function. The key state is divided into 3 types. The first is the initial state. The initial key I/O level is high. If the I/O detects a low level, it indicates that the key is pressed. At this moment, the current press time is recorded and the key state transitions to the pressed state. The second state is the pressed state. Since the system time system_tick continuously increments every 1.024 milliseconds. When the difference between the system time and the press time exceeds 10, it indicates that more than 10 milliseconds have passed since the key was pressed. At this point, the debouncing is complete and the key I/O level is in a stable state. The I/O level is then read. If the I/O level remains low, it confirms that the key is indeed pressed. The third state is the released state. Similarly, when the difference between the system time and the stable level time exceeds 10, it indicates that the debouncing is complete and the I/O level is stable. The key I/O level is then read. If the I/O is at a high level, it means the key has been released, and the key state transitions back to the initial state. If the I/O is at a low level, it means the key has not been released, and the current key state is maintained. Additionally, if the key state does not belong to any of the three states mentioned above, it defaults back to the initial state. Similarly, the scanning method for the direction key is identical to that of the play key. Refer to the explanation of the previous function for details. Next is the key function. First, it checks the state of the play key. Once it is detected as pressed, clear the play key status flag. Then, determine the current state of the LED and change its operating mode accordingly. Next, it checks the state of the direction key. Once it is detected as pressed, clear the direction key status flag. Then, determine the current moving direction of the running lights and change their direction accordingly. Now let's look at the LED initialization function. This function includes the power-on configuration for the struct. Here, the LED's power-on operating state is defined as stopped, and the initial moving direction is set to left. The LED IOs are configured as output, with all LEDs set to high, which means all LEDs are in the off state. Additionally, LED struct variables are used as shadow variables for the actual IO levels, where hex 3E represents the lowest bit being 0, meaning the first LED to light up in the running light sequence is the rightmost LED 1. This function implements running lights using LEDs. The LED operating state is divided into two modes, running and stop. In the running state, the running light effect is displayed. The variable power_on is used to determine whether it is the initial startup state. If it is the first time running the lights, the first LED to light up is the rightmost one. Meanwhile, in the running state, the direction of the running light's movement, whether shifting left or right, is checked. If shifting left, it is necessary to use the shadow variable for the LED state, as mentioned above, to check the state of the leftmost LED. If it is 1, the variable index records this state. Then, the shadow variable shifts left, and the index state is transferred to the rightmost LED. Similarly, if shifting right, the variable index first records the state of the rightmost LED. Then, the shadow variable shifts right, and the index state is transferred to the leftmost LED. Finally, the LED states are updated based on each bit of the shadow variable. In the stop state, the current state is maintained. Next is the time-based zero interrupt function. The timer interval is set to 1.024 milliseconds. The interrupt service routine increments a counter on each trigger, which serves as the system time base and enables the implementation of timing functions. Practice results. After the MCU is powered on, all LEDs remain in the off state. When the K2 key is pressed, the running lights start operating, moving in the left direction. When the K1 key is pressed, the moving direction is toggled. Press the K2 key again to pause the running light effect. Experiment summary. This comprehensive experiment utilizes multiple peripheral functions of the HT8 MCU, including the following 5. The general purpose I/O, time base, pull-up resistor, the internal oscillator, and the WDT. The hardware knowledge includes hardware key debouncing and LED driving circuits. The software knowledge includes key debouncing methods, key recognition principles, and the running light implementation principles. Holtec has a professional service team to assist in development design and after-sales service. Please feel free to contact our business departments for more detailed product information and consultation services.